In this video, we're going to discuss compound inequalities. A compound inequality is just a statement that's made up of two simple inequalities joined by the word and or the word or. So for example, this is a compound inequality. The statement x is less than -3 or x is greater than 1. We're joining two simple inequalities with the word or. And if we graph this set of solutions on the number line, then here's what it would look like. So in order for a number to be a solution, it only has to make one of the inequalities true because we're using the word or. So if I tell you that I'm either going to bring candy to class tomorrow for everyone, or I'm going to bring cookies to class tomorrow for everyone, then if I only bring one of those, you're not going to be upset, right? I said I was either going to bring cookies or candy. So as long as I bring at least one of those, then my statement was true. So the same goes here. If the number satisfies at least one of these simple inequalities, then it's a solution. So for example, the number 2 is a solution because even though it doesn't make the first inequality true, it does make the second inequality true. So any number that's less than -3 is a solution, and any number that's greater than 1 is a solution. So when we go to write this in interval notation, then we need two separate intervals. So with our simple inequalities, all of these solutions were next to each other on the number line. They were all connected. It was just one span of numbers we were looking at. Here we've got kind of two different intervals with a gap in between. So the interval at the left end there can be represented with this interval notation. And then for x greater than 1, we would write that like this in interval notation. And so then, since we want to consider these two sets together as one larger set, what we use then is the union symbol. So in math, if we want to join two sets together to make a larger set, we use the union symbol. Okay, say we have this statement here, x is less than or equal to 2, or x is greater than or equal to 0. Okay, so here's 0, here's 2. So x is less than or equal to 2, or x is greater than or equal to 0. Now in this case, there are numbers that satisfy both of those statements. Right? For example, the number 1. If you substitute 1 into the first inequality, it's a true statement, 1 is less than 2. And if you substitute 1 into the second statement, 1 is greater than 0. That's also true. So the number 1 is a solution. We count anything that satisfies one or both of the inequalities. So in math, what we say is we're using an inclusive or. In the English language, we have kind of two different versions of or. We have an inclusive and an exclusive. Inclusive includes the possibility of both. So it's like one or the other or both. That's what we mean by an inclusive or. So if I said I'm going to bring candy or cookies tomorrow, and I showed up with both, nobody's probably going to be disappointed by that. So that would be an example of the inclusive or. In the English language, we sometimes use an exclusive or. So for example, if you're at a restaurant and they ask you if you want soup or salad, they don't really want you to choose both. You have to make a choice. That would be an exclusive or. We don't ever use an exclusive or in math. It's always an inclusive or. So all that to say, numbers like 1, for example, are solutions. So any number that's less than or equal to 2 is automatically a solution. So everything to the left of 2 and including 2 is a solution already. And then we have some more solutions coming from the second part. Anything that is at least 0 is also a solution. So we've shaded all the solutions on our number line, and we've shaded the entire real number line. So all real numbers are solutions to this inequality. Okay, let's talk about and. Now, with an and statement, both parts have to be true. If I said I'm bringing candy and cookies to class tomorrow, and then I didn't bring both of those, I only brought one, then my original statement would be false. So we don't want that. So in order for a number to be a solution, it has to make a true statement when we substitute it into each part of this compound inequality. So if we place -5 and 0 on our number line, anything greater than or equal to -5 is going to fall, at -5 or to the right. Anything less than 0 is going to fall to the left of 0. So to be a solution, the number has to satisfy both of those statements. So what we're seeing here is the numbers between -5 and 0. Right? Those numbers would be greater than -5 and also less than 0 at the same time. For example, -1. Right? If you substitute -1 into both of those statements, they're both true. That's what we're going for. So let me get rid of some of my doodles here. So to shade the solutions, 0 is not a solution because it would make this second part false, right? 0 is not less than 0. But -5 is a solution because we're allowing for equality in that first statement, and it also satisfies the second statement. -5 is less than 0. So -5 satisfies both statements, but 0 only satisfies the first one. So 0 is not a solution. -5 is, and we said everything between them is a solution. And so this is what our interval notation would look like. Another way to write an and inequality, sometimes we write it without the word and because we'll write something like this. So that's another way to write an and inequality, is by kind of sandwiching it between two numbers. Okay, now if we have this statement here, x is greater than or equal to 10 and x is less than or equal to 7. And we're looking at our number line for solutions here. It's an and, so in order to be a solution, the number has to satisfy both parts of the inequality. So if we check, we kind of have three sections of the number line here. Right? We've got numbers less than 7, numbers between 7 and 10, and then numbers greater than 10. Anything less than 7, so over here, is not going to be a solution because it fails the first part, right? For example, the number 6. 6 is not greater than or equal to 10. So numbers to the left of 7 are not solutions. 7 itself is not a solution for the same reason, right? 7 is not greater than 10. Numbers between 7 and 10 are also not greater than 10. So it has to be greater than or equal to 10, right? So anything in these first two sections is automatically out because it's not greater than or equal to 10. Okay, well what about 10 itself? 10 itself satisfies the first one, but not the second one, right? 10 is not less than 7. And if we choose a number greater than 10, like say 11, that's also not less than 7. So we can't find any solutions. There aren't any solutions to this statement. You can't find a number that is both greater than or equal to 10 and less than or equal to 7. You can't find a single number that makes both of those true. So this one has no solutions. So when we're asked to solve a compound inequality, we might need to do some work to get the variable by itself. So for example, if we're going to solve this inequality here, then we need to isolate the variable. The steps for doing that are just going to be the same as for equations. So we can multiply both sides by something, we can divide both sides by something, add and subtract. This is the same as when we did simple inequalities as far as when you need to flip the sign, right, for multiplying or dividing by a negative. Okay, so here we would have, so basically you solve each part separately, each part of this inequality separately. And don't forget to remember if it's an or an and, because that's going to make a big difference, as we'll see here in a minute. All right, over here I'm going to subtract 1. And then, since I have to divide by -3, I'm going to change the direction of the sign there. All right, so we end up with this. X is less than 8 or x is less than -1/3. And it's important to know that it's the word or, because anything that satisfies at least one of those is a solution. So with the ors, it's kind of easy to graph. You just graph one inequality and then graph the other one right on top of it. Anything that gets graphed at least once is a solution. So x less than 8 would look like this. And then x less than -1/3, switch colors here, that's going to look like this. Well, we just graphed right on top of the solutions we already had, right? The stuff to the left of -1/3 happens to work for both. Okay, so those numbers are solutions. -1/3 itself doesn't work for the second one, but that's okay because it worked for the first one. Same with numbers like 0, 1, 2, right? So anything that gets shaded at least once is a solution for an or inequality. Now, what if we had the same problem, but it was an and? All right, so the steps for solving this would be the same, right? On the first inequality, I'm going to multiply both sides by 4 to clear the denominators, etc. So, each simple inequality looks the same once you isolate x, but now we have the word and instead. So, what does this look like? Well, when it's an and, the number has to make both statements true in order to be a solution. So, for example, the number 0 is no longer a solution because 0 is not less than -1/3. So now all of a sudden, none of the numbers between 8 and -1/3 are solutions. Only the numbers less than -1/3 are solutions because they work for both, right? If you go back to this picture, when I shaded the first part in blue and the second part in red, where was the overlap? The overlap was the stuff to the left of -1/3. Those were the only numbers that satisfied both parts. So when it's an and, the solutions are only the numbers that work for both parts. So in this case, all numbers less than -1/3. Okay, one final note on and inequalities. If it's written as a sandwich, I'm going to call it. So if we don't use the word and we write it like this instead, then to solve this, basically like we would usually do the same thing to both sides of the inequality. Here you're going to do the same thing to all three parts. So I'm going to multiply all three parts by the same number. And since that number is negative, I have to flip the signs. If I hadn't flipped the signs, right now my statement would say that 15 is less than negative 20. That doesn't make any sense. So it's good to check those kind of things. Make sure that if you look at the number on the far left and the far right, make sure the signs in between them actually make sense. And then same thing, we're just going to add 4 to all 3 parts. So we have 19 is greater than or equal to x, and x is greater than negative 16. So the numbers that are solutions are in this interval right here.